Welcome. There's a midterm today. Sorry. Hurts me more than it hurts you. Okay. On the board up there is a little chart about different things that are in the tree family. And they're divided in two categories, two ways each. So there's a kind of tree in which every node has a specific left child and a specific right child, and that's it. And there's a kind of tree in which a node can have any number of children. So that's the category that's labeled across the top, 2 children or n children. And then the vertical axis of this chart, you can build abstract data types for this kind of tree, or sometimes you're just using regular old pairs to make regular old lists, but you're using the ideas of this week about trees to think about those lists. So we've looked at the abstract data type capital T tree, the kind with datum and children as selectors. The book spends a fair amount of time on the binary tree abstraction. And we also talked about deep lists, about seeing a deep list, remember, as being a kind of degenerate tree in which the branch nodes have only children, no data, and the leaf nodes have only data, no children. And so we write programs, instead of writing programs like tree map that say make tree, something about the datum, something about the children, it's either or. We say if this is a leaf node, then do something about the thing viewed as a datum. If this is a branch node, which is to say it's a pair, then do something about this node viewed as a list of children. So the last piece of that chart that we haven't talked about is car-coder recursion, which I am going to get to, I guess, right now. So let's take my favorite list of lists. Okay, in the interest of time, I'm going to abbreviate. Okay, so this is a list of 4 elements. Each of the 4 elements is a list of 2 elements. And those things are words. Okay, everybody with me? So you got it that this is a list of length 4, right? And that each element of that list is a list. Now what I'm going to do is I'm going to grab this by its start arrow. I'm going to pick it up off the board and shake it. Okay? And the result will look like this. Wait, no, that's not going to work. I'm going to run out of room. Okay, so you see what I mean about picking it up and shaking it, and just sort of let gravity pull down this stuff. Because this, if I pick it up over here, it's really right heavy. So its right end is going to swing down, right? Okay. Speaking abstractly, what does this remind you of? A binary tree, right? Every node has a left child. Every branch node, which is to say every pair, has a left child and a right child. This thing is more like a capital T tree. So deep lists, and this is how we viewed it on Monday, as a list of lists. If you think list of lists, it's like the capital T tree in that a node can have any number of children. This node right here has 4 children, right? And this one has 2 children, and so on. Here, it's more like a binary tree. There's a specific left child and a specific right child for every node, even though these are exactly the same structure, right? I drew the diagram differently, but if you follow the arrows, you will find that there's the same number of pairs, and they're hooked up in the same way between these 2 diagrams. So what used to be the spine of the list is these 4 pairs, right? Okay. So I put up on the screen the most beautiful piece of code you're ever going to see so that you could worship it on your way in. But now I'm going to find, do I have, let's see, is any of this relevant? No. It's not. Sorry, just a sec. Yeah, that's the one I want. But no. Okay, never mind. Let's just put it up here. Okay. So up on the top of the screen, we have deep map rewritten. So we wrote a deep map last time that said, I can just type it in actually. It said define deep map list of lists. It said something like if pair list of lists then map, oh, whoops. That's what I meant. And child deep map function LOL, child over LOL. Otherwise, fin LOL. Okay? So this is deep map for trees viewed as deep lists. So we say, if what we're looking at is a pair, then we're going to take it as part of a list, and we're going to map, deep map essentially, over that list, the very list we have, because it's its own children. If it's not a pair, then it's its own datum, and we call fun on it. Okay, so that in the bottom, that's the deep list way of looking at structures made of pairs. Up at the top, though, we have a different version of deep map. Wait. Oh, no, that's what I just wrote. Duh, I'm an idiot. Sorry. Thanks. Right, here's the other version. The formal parameter is Xmas because that picture all the way on the right looks like a Christmas tree to me. So I'm reminding myself what shape it is. And there are three cases now to worry about. If it's an empty list, then I just return the empty list. If it's a pair, and here's the tricky part, then I say, okay, what is a pair? It's got a car and a cooter. It's basically, that's what a pair is. It's a car hooked up to a cooter. And so I can make the mapped version of this pair by calling deep map on the car and deep map on the cooter and consing those two things together. And I really don't care what kind of thing the car is and what kind of thing the cooter is. That's the job of the recursive call, to worry about that. I'm just going to take on faith that no matter what my car is and no matter what my cooter is, deep map will work on them, because that's the way recursion works. You assume that it'll work for anything smaller than the given problem. So I have these two subproblems, one for the car, one for the cooter. I call deep map for each of those, and I cons those two results together to get my result. Okay? So that's called car-cooter recursion. It has the disadvantage compared to the top version that it doesn't really respect the list structure. Okay, the top version really understands that a list is a string of pairs with elements in the cars, whereas the bottom version doesn't know anything about lists particularly. Because the bottom version, unlike the top version, doesn't call map. See, in the top version, if we're looking at a list, then we use map, which is the plain old function for plain old sequences from last week, to go through the spine of the list and apply the function to each car along the way. In the car-cooter version, there's no call to map. There's just these two recursive calls to deep map. One for the car, one for the cooter. And that's like what we would do for a binary tree. For a binary tree, we would say something like, make binary tree fun of datum of this node, deep map of left child of the node, and deep map of right child of the node. Right? We would call deep map recursively exactly twice, once for the left child, once for the right child. And that's what this does, except instead of making those things arguments to an abstract constructor, make binary tree, we just cons those two results together to make a new pair. Okay? Yeah? Okay, his question is, if cons, car, and cooter are used as constructor and selector for lists, why doesn't the second one have the idea list in it? So one answer to your question is, imagine a structure hooked together out of pairs that isn't a list or has pieces of it that aren't lists, which is to say there are pairs whose cooter is something other than the empty list or a pair, right? So you have like 2.3, that kind of pair in your structure. This second version, the car-cooter version, will happily work on that. We can say deep map square cons2 3, and we'll get the result 4.9. Okay? So this thing doesn't care anything about how you hook the pairs up. So I just said a moment ago that that's its weakness, but it's also its strength. So it's a little bit more general. Whereas the first version, because it calls map, and map works on the assumption that all the actual information is in the cars of the spine. So that's making an assumption that only works for lists of lists. You know, however deep you want, but they all have to be lists for it to work. So they're both valid. You know, they're both really good techniques. Neither one of them respects abstract data types. So I think I said last time that in that particular example about Don, Paul, George, and Ringo, what I have that really is a list of sentences. And I would probably, if I'm just manipulating things that are that shape, I would write my code that way, to know that they're exactly too deep, and the first thing is a list, and the second level is sentences. These techniques are good for sort of heterogeneous data structures, that they're different depths at different places. So you want to use something like tree recursion, but the abstract data types that they represent are something other than a tree. You wouldn't use either deep list recursion or Calcutta recursion on a capital T tree or on a binary tree. You would use the correct selectors and constructors for that abstract data type. This is for the correct selectors and constructors are something about a database. Right? We have a database over at Sproul about students, and it has a record that consists of your name and your student ID and your last known address and your transcript, which is itself a list of courses and grades, and your courses you're taking this semester, which is another list, and how much you owe the cashier and stuff like that. Right? And so it goes different depths at different places in that structure. And now I want to go through and make everything capital letters, because some software, the comparisons fail if some uppercase and some lowercase letters. So I'm going to totally ignore the abstract structure of this list, and I'm just going to treat it as a kind of degenerate tree. And I would make a choice whether I want to treat it as a degenerate n-children tree or a degenerate binary tree, and they both work. Okay? Really, the key things about these techniques is that they involve tree recursion. Okay, in the case of the one we did last time, the tree recursion is hidden in this call to map, because map's job is to call this function, which involves a call to deep map, once for each child of a branch node. So this call to map turns into several calls to deep map. Okay? In this case, whoops. What do you mean unbound? Thank you. In this case, at each time through this function, we make exactly 2 recursive calls. One for the left, one for the right. But that's enough for it to be tree recursive, for it to have the full generality of infinite depth of data structures. Okay? So when you see 2 recursive calls like this, you know that you're dealing with a tree recursion. Is that a hand up? Yeah. Right. I'm sorry, say again? The order of growth of all of these things is proportional to the number of nodes. Okay? Because you have to visit every node. Now, what counts as a node is slightly different. You know, whether you think of a pair as a node or you think of a whole list as a node, but it's going to turn out not to matter. Basically, all of these things have the same order of growth. Trees get you a better order of growth when you don't have to look at every element. So last time I showed you a binary search tree, and the whole point of the binary search tree was that in each comparison you get rid of half the remaining data, right? And so that gave me a running time of proportional to the depth of the tree rather than proportional to the total count of the tree. So typically log n rather than n. But
If we're traversing every node, then it doesn't matter how it's arrayed. We still have to get to every node. Okay. Okay. So I've just finished telling you that if you see two recursive calls, you're looking at a tree recursion. And there's either explicitly or implicitly a data structure that looks like those involved somehow. Now I'm going to show you not to get too hung up on form rather than meaning. Because this is a procedure you've seen before. This is filter. This is like the list version of keep, right? And it has two recursive calls. One here, one here. Is this a tree recursion? Take a vote. I want to see every hand. Who says yes? Who says no? Good. All right. Yeah, no is correct. Somebody who said no, why not? Yeah, because only one of these two recursive calls is going to happen any particular time through this. So either the predicate returns true, in which case we only do this recursive call, or the predicate returns false, in which case we only do this recursive call. There's no situation where we do both of them, as opposed to down here, where we always do both of them. Okay? So don't think, oh, if I see two recursive calls, that makes it a tree recursion no matter what. What makes it a tree recursion is the two recursive calls are actually performed. Right? So almost the very first program you saw in this course was a tree recursion, namely count change. Right? Can you remember back that far? Makes two recursive calls, one for supposing we do use a quarter, and one for supposing we don't use a quarter, or a dime, or a nickel, or a penny. Right? And we add up the results of those two recursive calls. So that's tree recursive. Now, is there a tree involved? Is there a data structure in the computer that's tree-like? No, not in count change. In count change, the tree is implicit. It's like I have $1.37 and my biggest coin is quarters. Okay? And then it's a binary tree. Either we have $1.37 and the biggest coin is dimes, or we have $1, can I do this subtraction in my head, 12, using quarters. Okay? And so on down. All right? That data structure doesn't exist as a data structure in memory, but it's in the programmer's head. It's implicit in the program that there's a control structure that has that shape for this problem. Okay? So it's tree recursion whether there's a concrete tree involved or not. So tree recursion is a very important thing to understand. It's pretty hard. Some people had trouble with it back in the first week. Some of those people have since dropped the course. But probably some of the people who had trouble with it are still here. And if so, now is your chance to really learn it and understand it. So don't let yourself get past this week not understanding tree recursion. If it's a problem for you, get help from me, from your TA, from HKN, from somebody. All right. Tree traversal. Okay, so the topic is, I have a tree, and I'd like to visit every node. And let's see. Where is this? Does it say in my notes? Search. Is there a search? Yes, there is. Yay. Okay. So let's say we have a tree. It's a capital T tree. It's an abstract tree. And we have, I don't know, losing my mind. Oh, Roger, that's right. And Ray, and Dave, and Pete, and Nick. Okay? Whatever, it's a tree. My job is to go through this tree, printing out the datum of every node, one per line. Okay? Well, there are two basic ways I can do that. They're called depth first and breadth first. Depth first says, okay, I've printed out the word music. Now what I'm going to do is look at the first child. So far we could be in either breadth or depth first. And when looking at the first child, it's a tree, and I'm going to look at the whole thing. So the datum at this child, I'm going to print Beatles, then I'm going to print John and Paul and George and Ringo. And then when I'm complete, and if some of these had grandchildren, I would print them too. Then when I'm totally finished with this tree, then I move on to the next sibling. So it goes down before it goes sideways. That's why it's called depth first, tree traversal. Okay? The program to do it is very simple. It's the first three lines at the top of the screen. So to depth first search a tree, and here all I'm going to do is print out the datum of each node. So I start by saying, print the datum of this node, music. And now I'm going to say, for each of the children, depth first search them. So I'm going to depth first search Beatles, which means I'm going to print Beatles, I'm going to print John, Paul, George, Ringo. Then I'm going to depth first search Who. And I'm going to print Who, Pete, John, Keith, I forgot again, Roger, thank you. I am so getting old. And then after I finish that tree completely, I'm going to go into kinks, and I'm going to do Ray, Dave, Pete, Mick. Okay? That's it. That's very simple. And the reason it's so simple is that my processing of the tree is following the actual links. Okay, because there aren't any links from sibling to sibling in a tree. The linkage is all child to parent, parent to child. So in order to get from Beatles to Who, I have to sort of think sideways. Right? Whereas in depth first search, remember each child, here's the real point, each child of a tree is a tree. So if I do a recursive call for the child, it's going to do that whole tree. So for each, calls depth first search for each of the children. And that's the pattern that I get. Breadth first search is a little more complicated. To do breadth first search, I have to invent a data structure that's going to remind me where I'm up to. So the goal of breadth first search is I want to print music, Beatles, Who, Kinks, John, Paul, George, Ringo, Pete, John, etc. Okay? So go all along one level and then go down to the next level. So to do that, I'm going to have a queue. Q. There was an XKCD last week about words with a lot of vowels. That's one of them. So for the purpose of this exercise, something with a triangle drawn around it means the tree that has this as its root datum. So to start with, my starting conditions are going to be that my Q is empty. Okay? And I'm going to call breadth first search iter. It's an iterative algorithm. Oops. Here it is. And, oh, I'm sorry, my queue is not empty because I call breadth first search iter with list tree. A queue is just a list. I'm going to stick things in at the back and pull them out at the front. So my initial queue is the music tree. Okay, that's my queue to start with. Now, what do? I say, is the queue null? No, it isn't. So now let task be car of queue. So task over here is going to be the tree music. Now, what does it mean to deal with this task? Well, so I'm down here. Oops. There's got to be, oh, I see. I'm pushing the wrong button. There we go. So I'm going to print the word music. And now I'm going to make a recursive call with a new queue in which I append cdr of q, which is what? What's the cdr of this? The empty list. It's not a tree at all. It's a list. The queue is a forest. It's a list of trees. So if I take cdr of this queue, it's empty. So I'm going to append to the empty list children of task. Task is a tree, so it has a children. What are the children? There's the Beatles tree. There's the Who tree. And there's the Kinks tree. Okay? So that's my queue. Now I'm going to say, I'm making the recursive call to BFS iter. Is this queue empty? No. So let task be car of queue. So task is now the Beatles tree. And what do I do for this task? Well, I print datum of the task, which is Beatles. So I printed music, I print Beatles. And now I append cdr of q, which is now more interesting. It's not empty, right? It has Who and Kinks in it. And to that I append children of task, which is the John tree, the Paul tree, the George tree, and the Ringo tree. Okay? So that's my new queue. Now I take car of q, that's Who, that's the task. The new queue is Kinks, John, Paul, George, Ringo, Pete, John, Keith, Roger. I got it this time. Okay? So do you see how this generates a depth first search? I'm going to handle all the siblings of Beatles before I handle any children, because all I do with the children is stick them at the end of the queue. End means I'm going to get to them last, right? Because I'm taking things off the front of the queue. Queue, by the way, if you don't know the word, is British for line. as in standing on line at the bank. That's what a queue is. So things come in at the back and they come out at the front. Otherwise known as last in, last out. First in, first out. Yeah, first in, first out. That's a queue. Okay. So this procedure, it's only a little bit longer. It's 6 lines instead of, 8 lines instead of 3 lines. But it's a lot more complicated because I need this auxiliary structure called a queue. I have to understand how that works. Notice that, by the way, as an exercise in data abstraction, we use car and cdr for the queue, but we use datum and children for the task because each task is a tree. Whereas the queue is not a tree, it's a forest. Okay, so don't make either mistake of data abstraction. Too many datums or too many cars. Okay. Why would I want to do things in either of these ways? Well, depth-first search, mostly, to be honest, you do depth-first search when you really don't care what order it's in. And depth-first search is just easier because you're going with the flow of how the language represents things and using higher-order functions like map to help solve your problem. So it's just easier. But also, you want to do it depth first because you want to group things that are related. So if we're printing out this tree, it's actually much more sensible to say Beatles, John, Paul, George, Ringo, Who, Pete, John, Keith, Roger, Kinks, Ray, Dave, etc. Okay, so put the group name and then the people in the group, rather than the 3 group names and then all the people in a row. It's more informative to print it out depth first. Okay? Why would we ever want to use breadth first? The answer, broadly speaking, is about searching of some space of possibilities. And the canonical example is I'm writing a program to play chess. So I hope you all know that 30 years ago, chess was the canonical example of something that a computer will never be any good at. And today, the world's champion chess player is a computer. Not so much because we got smarter, but because computers got faster and more powerful. So how do those computer chess programs work? Well, the way they would work ideally is they would construct a complete tree of possible board positions. Right, so the beginning board position would be all the white pieces in these 2 rows and all the black pieces in those 2 rows. And then you'd take every possible move for white, and that would make a child node. And then each possible move for black, based on that move for white, would be the children of that, and so on. And you'd go all the way down until you reached leaves. And a leaf node would be somebody wins the game. Or you get in a cycle and it ties. And then you would work your way back up the tree, trying to figure out how we can force a series of moves that leads to me winning. Sadly, the number of possible board positions in chess is, I think this is true, greater than the number of atoms in the universe. So we aren't ever going to construct that tree in its entirety. And instead what happens is you build that tree breadth first to get as deep as you can before you run out of time. Because you only get a certain number of minutes per move in chess. That's why they have those clocks like in the movies, bam, bam. So you take almost all your time and you spend it building this tree breadth first, because you don't want to chase down a dead end and not get to some other possibility. So you have to look at all the possibilities at once. And then when you're almost out of time, you stop building the tree down and you start evaluating board positions. Right now, the board positions that you're looking at, nobody's won or lost the game yet. You're like 8 moves ahead of yourself or something. And so what you have to do is evaluate those board positions basically the way human chess players do, right? You say, what's my pawn strength, and how many points of captured pieces do I have, and all those questions that chess players ask. It's in the books. And so you come up with some figure of merit for each board position, and then you work your way up trying to force the best possible board position that you can force your opponent to give you. So making that tree is an example of why you would want to do something breadth first. Because if you do it depth first, you're going to run out of time before you have an answer. Okay? Another reason is it's not that you would run out of time, but you're looking for the minimal possible path to a leaf. Okay, so my favorite example of that is everybody take the kind of IQ test where they say you have a 3-court pitcher and a 5-court pitcher, and you're down by the river, and you're trying to measure 4 courts, and the pitchers aren't marked. How do you do it? And you can pour from one to another. All that. Those are pitcher pouring problems, and their trees are, quite simple, basically. So you could traverse the entire tree in no time if you're a computer. But the answer you want to come up with is the one with the fewest possible pourings from one thing to another. And the way to get the fewest possible steps to a leaf node is to do it breadth first. So can I find a leaf node one level down from my starting point? If so, finished. If not, construct my grandchildren. Can I find a leaf node in there? No. Construct my great-grandchildren, and so on. So that's another reason for doing breadth first search. Okay. You are going to get all of this in gory detail, writing the code to do it and everything in 61B. But I'd like you to kind of have the ideas at this point. Okay. For binary trees, within the general category of depth first, there are subcategories. So I'm going to construct the best example that I know for why these ideas are important about traversal, which was the parse tree that was like this that I showed you before. Okay? So now, to parse this depth first, for each node, there are basically 3 steps. There's print the node, there's do the left child, and there's do the right child, right? Those are the 3 steps. Well, we can do those 3 steps in basically any order. People always do it left to right. People who speak English, which is a left to right language, always do it left to right. I have no idea. Maybe if you're a Chinese computer scientist, you do it right to left. Anybody know? Anybody follow Chinese computer science? Anyway, it doesn't matter. For our purposes, we're going to go always left before right. And that reduces the number of interesting possibilities to 3. And the 3 possibilities are, in order, left, bottom, right. And that gives you 3 plus 4 times 5, right? First I print the 3, then I print the plus, then I do an in-order traversal here, which means first the 4, then the times, then the 5. So that's in order. Next we have pre-order. Also very interesting, where we say datum, then left, then right. That gives us plus 3 times 4, 5, which 2 months ago you might not have thought very interesting, but now you can see is sort of the center of the universe. And then finally, we have post order, where we say left, right, datum. I think I showed you this actually, which gives us the peculiar result 3, 4, 5 times plus. For human purposes, that looks pretty bizarre, unless you have an HP calculator, in which case you're accustomed to it and you understand the merits. But if you're a computer and you're running a PostScript, you're running a PostScript file to be printed, or JavaScript, do I have that right? No, JavaScript is prefix. Some language or other that's postfix. This is what you do. You get the data ready first, and then we say, what operator do I want to do? So this order, although it looks funny, is the order in which a computer actually carries out the computation. So we say 3, put that on a stack. A stack is the opposite of a queue. It's last in, first out. So take my 3, put it on the stack. Take 4, put it on the stack. Take 5, put it on the stack. Oh, look, an operator. Let me pop 2 things off the stack and use them as the arguments to times. And that gives me, of course, 20, which I push on the stack. And then, oh, look, an operator. Let me take 3 and 20 and give them to plus. So that's a really useful way to have things represented from the point of view of a computer. So those are the 3 sub-possibilities within depth first for binary trees. As usual, I'm not going to get to show you pathfinding. In my lecture notes, there's a nice example taking the world tree, asking the question, where's Berkeley? The answer to which is world, USA, California, Berkeley, that list. So that's a slightly tricky piece of code. It's just as well that I can't lecture about it because you wouldn't understand it from me doing it quickly, but you should read it in my notes. Next time on Friday, you're going to see your first scheme interpreter written in Scheme. And then Monday's a holiday, which means everything you're doing for project and homework is due Tuesday. Okay? I think some piece of the reader has that wrong. Okay, see you tonight, not here, 2050 VLSB.